Hi. In this video, I hope to wrap up my exploration of my timing issues here on the build and get the circuit to a state where I can move forward. If you haven't realized yet, I record my intro at the beginning and then turn around and build the content behind that. I don't turn around and record the intro at the end, knowing what the video is going to hold. That doesn't always work out. I've had to change gears and change tactics partway through the video. And, well, today I broke my glasses. I'll give you a better shot of this on the overhead. But I ended up having to actually put copper wire around it and solder that in place just to hold the glasses on my face. So I don't know that I hold out high hopes for this. In the first video, we took a look at the counter ICs, realized that what I had put in place was half the speed of what was available, so I upgraded those. In the last video, I went through and did some signal shaping, making sure that the signals were as crisp as I could get them. I still have a concern there, but I don't believe it's going to slow me down too much. And in this video, I want to now compare all of my signals to the clock to make sure that they're coming in at the right time. I believe I've got some challenges there as well. Let's get into it. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Okay, I want to start today with a look at the different types of signals that we're going to have to measure and make sure are shaped properly. The first of which is an assert to address bus 1. Now, currently I only have one thing that ever asserts to address bus 1, and that's the program counter. So as much as I'd like to take a look at that signal, I'm never going to actually be able to do that, at least not yet. The second signal to look at is the main bus assert. Now this is off of any one of several devices or registers onto the main bus where several different things can read from that. Now this is supposed to happen during the entire clock cycle, starting at the rising edge and ending at the subsequent rising edge where it could potentially be replaced with something else. And if you recall, this is where I have my concern related to the main bus assert returning to all zeros in almost a capacitance decay. But that's going to be the first signal that we look at here. The second set of signals that I want to look at is the entire load increment decrement cycle. Now those are all bundled together, and I will want to look at those in relation to the rising edge. It should be just a quick spike and then return down to a low signal, and that's the new spike clock that I've developed. I don't know exactly what to call it, but that's what I have called it. So I've got three different load increment decrement that I need to look at and make sure that those are all happening properly. The next signal I want to look at is the AND latch signal. Now this is supposed to happen on the falling edge of the clock, so that as that signal falls, the contents on the bus is latched into whatever register and then turned around and settled ahead of the next clock cycle. Now I also have an instruction suppress signal that I need to look at. I believe that is working exactly the way I need it to. This is the last signal that I will look at, the clear carry and set carry. I cannot test because I don't have the ALU hooked up at the moment. Okay, my yellow trace is hooked up to my raw clock signal here. The blue trace I'm going to drop into what would be my main bus assert signal on R2 over here. And zooming in just a little bit here, without actually getting in and measuring it, the delay looks like it's about 50 nanoseconds, give or take. And the shape of those signals looks really actually pretty good. So I'm not horribly concerned with that. The other one I want to measure is the fetch the fetch register assert, and that should be there. And again, that looks good as far as the shape of the signal is concerned, and the delay itself looks consistent. Now, if I go to the rising edge when it's deasserting off the bus, now this is going to take a minute because it's got to re-average. But once again, the shape of the signal looks pretty good. I'm at a 50 nanoseconds per division. That's not something that, it looks consistent. And if I hop over here, again, that looks quite reasonable. Now, that said, I'm still using LS logic here to drive HC logic. I want to replace each of these with an HC version, or this is already an HCT version, so that the family is the same and the outputs are the same, and I should then be able to drive everything with a slightly faster signal. But right now everything looks like it's balanced properly, and this all looks good to me so far. All right, let me switch up and we'll take a look at the AND latch signal. Okay, now the AND latch signal, I am expecting to go high with the falling edge of the clock and then come back low again with the rising edge of the clock following that. So let's see if we can find a place to measure that. So this is R2. And let's see here, we're measuring the rising edge on channel 2. And what I'm seeing is I'm seeing quite a significant delay here. I'm expecting that to happen with the congruent with the falling edge of the clock, but I've got a 150 nanosecond delay. What do we have on the program counter? A similar delay. And R1, about 130 nanoseconds-ish. I guess the question now is can I shore that up? All three of those AND latch signals are built into control ROM 3, which is here. Those are bits 7, 6, and 5, so the three most significant bits here. And so tracing those, these are NANDed. There's an inverter that goes on here, and then NANDed with a bunch of inverted, a significantly delayed clock. So I believe my program counter has some extra delay built into it, but it appears to be NANDed with the results of all of this delay here, which is driven off of the actual clock. I believe that's incorrect. So my clock looks like this, and my signal looks like this, and the result needs to look like that. So this is my clock, this is my signal, this is my target. That is NANDed with the clock delayed, and I believe that needs to be ANDed with the inverted clock. I need to get some components out. Okay, I was totally prepared to rip out this NAND gate and make changes, but then I realized that my default or unused state wasn't going to be properly represented. And the LEDs here are set to come on when voltage is 0. And therefore, in order to maintain this, the NAND gate is really the proper tool for the job. All right, so now if I look at my signal again, what can I do about this delay? And does that work? Okay, no, it does not. And the reason it does not is because the load and latch are having problems. The increment is working. The decrement appears to be working. It's simply the load and latch. So there's the load of R2. Program counter is not working either. So the increment and latch on the program counter is not working with that like that. Okay, that's an odd signal there. Why is that pulsing down and back up? Okay, there is definitely something going on here with the first instruction fetch is correct, but the increment and latch is not happening, which I thought was a good signal, the load increment and decrement. And I'm reading those in the correct sequence, so increment is going to be 2, binary 1, 0 on that signal. So reset. Well, that was correct. That's the correct signal going out. Compared to the clock after reset, it's going down. That is not the right signal. That should be a rising pulse, not a falling pulse here in the blue. I need to think this through a moment, but I believe that is ultimately what is my problem. And the question is where is the flaw? Is the flaw here or is the flaw here? Is the flaw in these register PCBs that I've made twice now? Or is the flaw in my control logic, which I have carte blanche to change? All right, I got to get a look at this schematic here. So my two register inputs, 0 and 1, go into the 74HC138. Outputs are do nothing, which is not tied to anything. Then load, increment, and decrement. The load increment and decrement also go off to light, or to the line drivers to light the LEDs associated with them. Again, like I said, those are VCC tied through current limiting resistors through LEDs so that the line driver syncs the current. All right, so back here on the overhead, here is my 138. And if I measure my increment, which is the third pin over, I'm seeing a fall in voltage. It's low for the whole time, for the whole period. What does R2 do? That is the signal I'm expecting to see up here on the program counter. That is not the signal I have up here on the program counter. So why not? All right, so bits 5 and 4 on control ROM 2. So control ROM 2, and I'm looking to see which of these two are the ones for program counter, and they are ANDed with the clock, and then they go directly out. These two are for R1, which is not being used. These are ANDed with the clock and go directly out. So that is incorrect. Now, coming back here, I have these three for R2. Back to the overhead. These are coming off of control ROM 3. So up here, these are bits 4 and 3, which come down here on this clock. So these two need to be operating off of the same clock, and they are not. So this has to come out. And this then gets plugged in here. Let's see how that works. Okay, I got my load increment. That worked. That loaded properly. Increments and decrements are working correctly. And that is the signal I am anticipating I should be seeing. So I was shaping the program counter differently in R1, actually differently than R2. But now that I have everything congruent, I'm good. Now I have not tested R1, but I think I've got it traced down pretty darn good here. That can go away. Now, while I'm here, I believe I have completely eliminated all of this delay here. So this 74 LSO4 inverter, this 74 LSO4 inverter, that's 12 inverters I've taken out of this setup here. So let me see what the AND latch signal now looks like. And I've still got a funky AND latch signal going on here. I'm not sure what that's related to. I believe that's related to the jump. So let me see if I can single step my way through that. Yeah. That's related to the jump. So I got to figure out something related to that. I believe I can pull, let's let it run. I believe I can pull all of this with no change in behavior. I can pull this line with no change in behavior. And I believe I can pull all of this with no change in behavior. Okay, the last thing I want to make an attempt to remove here, besides my oscilloscope, is this delay in the reset logic. Now, the 74LS74, I have this hooked up to the Q output here. And then I threw a bunch of inverters in order to delay that. If I take the inverted Q output and drop that into here, and then when I reset, I actually now get the first instruction fetched. Whereas if I have it in the Q output, it does not. And that's because the latch associated with program counter has to actually latch properly ahead of the fetch here in the EEPROM memory. So this can go away now as well. Just do a reset to make sure. Yep. Let me see if I can get that 74LS04 out. Okay, so another reset, and that works just fine. Yep, that's working exactly like I need it to. Well, I was getting ready to record the segment where I would check the instruction suppressed signal coming into my fetch register, keeping it from passing on to the instruction register. And disaster struck. My oscilloscope stopped working. It first turned that it would power itself off indiscriminately. And then when I disconnected the battery and hooked it up to USB line here, now it just gives me this mess of a signal. Now I know my signal is good here and I've got it plugged in here, but no matter what I do here, nothing works. So now I'm without an oscilloscope trying to probe around and determine if there's anything that I can do to improve these signals. And this is no longer going to be useful. I guess it's time to upgrade. Okay, well, this has turned into quite the show today. As long as you can get past all of the different noise elements, I think I've got this working well enough that I can actually take this measurement. Tomorrow might be a different day. But I've got the... Well, let me move this. I've got the instruction suppressed signal here. And if I look at the timing of that, let me switch my trigger to be channel 2. On the surface, that seems to follow the entire clock cycle. If I now zoom in, and I've not done this, so I don't know just how close that is. 50 nanoseconds per division. Let me let that average back out. And I look like I'm running about 25 nanosecond delay. Now if I switch to the falling edge, again, that could be about a 25 nanosecond delay. That instruction suppressed signal looks pretty good to me. So now the next thing is what's going on with that jump. And I will tell you that it's not hurting anything. It's not technically correct, but it's not hurting anything at the moment. And I don't have anything robust enough in order to be able to track that down. I do have a Heathkit 2-channel oscilloscope. It's an old analog, and it has an old CRT in it, but there's no high voltage. The high voltage does not actually come on. There's nothing that's being shown on the CRT, so I have to get to the bottom of that. I did make an attempt to get it running today without success. Well, it turns out that my glasses was not the worst thing that happened today. Losing the oscilloscope is going to be a big blow at the moment. I do plan on replacing that with something newer and something a little bit more robust, but it's going to take a little bit before I can actually make that happen. Overall, I'm thrilled today. Unfortunately, I did end up cutting the video short just a little bit, but getting those signals shaped properly, I believe, is going to remove a lot of concerns moving forward. And the next video, what I need to do is I need to take control ROM and the 2 boards that are associated with that and get those revamped. I want to replace the LS logic with HC logic so that we get that being driven properly at the right speeds. And later we can come back around and reevaluate the shape and timing of those signals, but I think it's going to overall improve the stability of the circuit as well. We'll see you soon.